Hi class, welcome to Wednesday, April 28th, period 4, day 18 of Coronachem. We're starting a new period, we're starting a new subject, a new chapter really, extending the subject. It's the chapter that deals with buffers. And what you can do to supplement your learning, in fact this is probably the most important thing you can do today. I'd like you to find the playlist that's in my site titled Acids and Bases and watch parts 6 to 9. You already know parts 1 to 5. If you don't know the parts 1 to 5, you should watch that as well, but I think you already know that. Watch parts 6 to 9 and also the last video in that playlist, which is entitled How to Calculate pH at the Equivalence Point. So 4 or 5 videos you should watch, definitely. This chapter starts off with the notion of the common ion effect. The common ion effect tells us that the ionization of a weak electrolyte is decreased by adding to the solution a strong electrolyte that has an ion common with the weak electrolyte. So you can suppress the ionization of a weakly soluble salt or even a moderately soluble salt by the addition of a strong electrolyte which interferes with further dissolution because it participates in the equilibrium process. You can calculate the final concentration of the dissociated salt in the same way that you would do the calculation for a weak acid, but what you do is you add in the initial concentrations of whatever ion is present that interferes with the ionization of the salt. So in the case of nitrous acid, I have a practice example in the text. This is on page 723. The question asks, calculate the pH of a solution containing 0.085 molar nitrous acid, HNO2. It has a Ka of 4.5 times 10 to the minus 4. And 0.1 molar potassium nitrite. So the potassium nitrite, because it's 0.1 molar, releases some ions into the solution before the acid even begins to dissociate. I'm going to adjust the camera so you can see the calculation. There you go. So I set up an ice table. Here's the dissociation of nitrous acid. And you get proton and nitrite. By the way, this is probably the first time in history that a class was taught using a refrigerator. So if you'd asked me a month ago whether I would ever foresee myself teaching on the refrigerator, I would have looked at you as though you were crazy. Well, here we are, thanks to coronavirus. Anyway, you start off with 0.085 molar of the nitrous acid and 0.1 molar of the nitrate from the strong electrolyte which is already dissolved into solution. That's the potassium nitrate. So this concentration is being furnished by the potassium nitrate, KNO2. So the presence of the potassium nitrite is already producing 0.1 molar of nitrite ions. So then we set up the same way as we usually do with an ice table. A certain amount X of the nitrous acid dissolves. So at equilibrium we have 0.085 minus X. And the H plus concentration starts off at 0. A certain amount X dissolves of the nitrite, the nitrous acid. So a certain amount X of protons is also going to appear in solution. And at equilibrium you're going to have a nitrite ion concentration of 0.1 plus X, because you already had 0.1 sitting in solution. More is released from the nitrous acid, that's represented by X, so at equilibrium it's 0.1 plus X. Ka is 4.5 times 10 to the minus 4. This represents the nitrous ion concentration, this represents the proton concentration, and the denominator represents the nitrous acid that's been dissociated. Set up a trinomial enter the values into your calculator on the quadratic function, and you get a value of H plus concentration x1 is equal to 3.79 times 10 to the minus 4. The other value is negative, so you can discard it. When you enter that into the pH equation, pH equals negative log of 3.79 times 10 to the minus 4, you get a pH of 3.42. Now, you don't have to use the quadratic formula on your calculator. You can just simply use it the old-fashioned way, where you enter the values into the quadratic formula. If you don't recall, it's minus b plus or minus square root of b squared minus 4ac all over 2a. So where a, b, and c represent the coefficients in front of the trinomial. The next idea I want to mention is buffers. Buffers are when substantial amounts of a weak acid and its conjugate base are added to a solution. Then what you get is a buffer. Buffers resist changes in pH in both directions. They're useful for maintaining a pH at a specific level so that you can regulate the speed of certain reactions. Our body has two buffer systems. We have a bicarbonate buffer and a phosphate buffer in our bodies to help maintain the pH very strictly between 7 and 7.4 roughly, because our enzymes only work properly in that very tight pH range. So the human body has to maintain that pH in that very narrow range, or else things start to go wrong. So there's an equation that you can use whenever you have a buffer system. I mean, there's the old-fashioned way of solving it, where you solve for H plus concentration using an ice table, and that works fine. You get the correct answer. But when you have a buffer system, you can use the definition of Ka to come up with an equation where you simply plug in the concentrations of the acid and its conjugate base, along with the Ka, and the Ka is modified. There's a term called pKa. It's the same as pH, except it's applied to the Ka, so it's the power of Ka, if you want to look at it that way. And it helps you to solve for the pH when you're using buffers. One interesting fact about pKa: when the pH equals the pKa of a certain substance, you've reached the point at which half of it is ionized. So this is something that's useful to biochemists, because biochemists frequently do assays where they actually separate proteins out based on their amino acid composition. So they pre-digest the proteins, and then they apply current, and the different amino acids separate themselves on a gel, and each protein has its specific fingerprint, if you like, and it can be used to characterize the content of proteins. But let me show you how to derive the Henderson-Hasselbalch equation. I'm going to try to erase this. I don't know how well that works. Not well at all, apparently. I'm going to really apply pressure. I'm going to have to use some water. Luckily, water is available. Okay. A little alcohol to clean it up. And it's almost as good as new. Okay, so what I'm about to develop is called the Henderson-Hasselbalch equation. you will eventually be asked to show the derivation for this. Start off with the definition for Ka. Ka is equal to the, for the weak acid that is, Ka is equal to the concentration of proton times its conjugate base over the concentration of undissociated acid. You can begin to rearrange the equation by transposing the HA to the Ka side by multiplying both sides by HA, so that you get Ka times HA equals proton concentration times conjugate base concentration. Now, if you isolate for the H plus and put it on the left side, you'll get this. H plus concentration is equal to Ka times the undissociated acid concentration divided by the its conjugate base concentration. Now we're going to take the negative log of both sides. Take the negative log of both sides. Negative log of H plus concentration is going to give you, I'm just going to write, I'll rewrite every step so you don't miss anything. Negative log is equal to negative log of Ka times HA over A minus. Now, when you flip this over, it becomes the opposite. For example, if you take the power of 3, say if I said x to the power of 3, I could rewrite it as 1 over x to the power of negative 3. So we're going to do the same thing here. When we flip this over, the powers become negative. So you can subtract it. Simplifying, we get pH equals pKa minus the log of A minus over HA. And then because I'm allowed to, when I flip it over, I change the sign on it, this negative log becomes plus log. I would have shown you into reading the step, but I ran out of space on the board. So this is called the Henderson-Hasselbalch equation. pH of a solution in which there is a buffer, meaning a solution that contains both the acid and its conjugate base. You can determine the pH by finding the pKa of the acid, and by adding to that pKa the log of the concentration of the conjugate base and the actual acid. Now let's see if we can show you a little example of using the Henderson-Hasselbalch equation. This is on page 727. This erasing part is not convenient. Let's see if this works better. Actually, that does work nicely. After this, I'm going to have the cleanest fridge in the city. One more. Hopefully you finish copying. If not, you can pause it and rewind a bit. That's odd. Get the last bits off. Whoa. What I need is a real whiteboard. Okay. So on page 727, there's a practice example where you get to use the Henderson-Hasselbalch equation. It asks, calculate the pH of a buffer composed of 0.12 molar benzoic acid and 0.2 molar sodium benzoate. Alright, so the pKa, the Ka of the acid is 6.3 times 10 to the negative 5. Benzoic acid looks like this. It's used as a preservative. They put it in bread and many other things. I think what it does is it sequesters metal ions and it prevents the bread from going bad. It extends the shelf life of certain foods. So we're going to do it by using an ice table. And then we'll use the Henderson-Hasselbalch equation to show you how quick it can be done. So this is benzoic acid. This is the benzoate anion that results when the labile proton ionizes. And then you, of course, get the proton. So you start off with 0.12. A certain amount of X dissociates. At equilibrium, you have 0.12 minus X. Benzoate ion concentration starts off at 0. X amount dissociates, and at equilibrium, you have X sitting around in solution. And same with the proton. So the Ka, which we looked up at the back of the book, is 6.3 times 10 to the negative 5. We set up an equilibrium, x squared over 0.12 minus x. The trinomial that results is x squared plus 0.2, then 3 zeros, 6, 3x, minus 7.56 times 10 to the minus 6, all that equal to 0. Plug that into your calculator using the quadratic formula function, and you will get the following two numbers: 3.778, 0.962 times 10 to the negative 5, and negative 2.0010078 times 10 to the negative 1. You're going to discard the negative result. This is the one that you want to use. That's equal to your value of X, which is equal also to the concentration of H+, from which you can calculate the pH. pH equals negative log of the H+ concentration, and after sig figs, what you get is 4.42. Now let's solve the same problem using the Henderson-Hasselbalch equation. And you get pH equals pKa plus the log of the conjugate base concentration over the acid concentration. pKa, we looked it up. Well, we looked up the Ka. When you take the negative log of the Ka, you get the pKa, which is 4.2, plus the log of the concentration of the various did I write? Just a minute. Oh, 0.2 molar sodium benzoate. I forgot to write that part in. Sorry, this part is wrong. I mean, I did it right, I just wrote the wrong numbers up here. Right, so this is the actual formula. It works out correctly, and then of course I wrote this wrong. This part is, okay, there. Now it's okay. This part is correct. I copied up, I just did this, I shot from the lip a little too fast, so just sorry about that. So using the Henderson-Hasselbalch equation, we plug in, we find out that K is 4.2 because the K is 6.3 times 10 to the negative 5. Take the negative log of that, you get that. And then plug in the concentrations of the A minus and the HA, which is, in this case, 0.2 and 0.12. What you get is a pH equal to 4.2 plus the log of these two numbers, which gives you 0.221848, which gives you a pH equal to 4.42. Same as with the ice table. You should be getting the same number because it's essentially the same calculation. So I'm going to stop there for today. You have your work cut out for you. Your real work tonight is to watch parts 6 to 9 and the video titled How to Calculate pH at the Equivalence Point. And then we'll pick it up from there tomorrow. This is all chapter 17. Okay? See you tomorrow.